if you see on the right here, a good 80%, if not 90% of all the disasters, including the geology-oriented or coast disasters such as earthquakes or tsunamis or hydrometeorological disasters or avalanches included, water is the biggest killer in this regard. And somehow, subjectively, people feel that something is wrong out there with the hydrological system. It doesn't behave the same way as it used to. Therefore, a couple of questions are being asked in this regard. First of all, is it really true that the hydrological cycle is accelerating? Because if it does, then the probability of the extremes at both ends will be increasing. There will be more frequent floods, but in order to keep the continuity at work, there will be more extensive droughts, both in space and time. Does this include and involve an increasing risk? No doubt. If the hypothesis which the profession is entertaining, that the cycle is accelerating, then there will be an increased risk. Natural risks, but also human risk, because people have the tendency to move back to the same area. That has a great thing to do with the social fabric of a society. Take, for instance, the case of Pakistan, which I will mention briefly. Is there a growing vulnerability of our systems in stock? And the answer is definitely yes. The big question is, which is what we are now analyzing, is whether really there are more disasters in stock or not. And if there are, then we have to start preparing to mitigate the impacts of those disasters. It's a multi-decadal program. It doesn't happen overnight. It's from the design of a prevention system or a mitigation system up to the building. It takes decades. Will there be less water for people? That's definitely true. Because if you look at, and I'm not going to bore you with statistics, if you look at only one data, the per capita water availability, 35 years ago, the per capita water availability, grosso modo, globally, was about 13,000 cubic meter per person per year. Today, it's down to 5,000. Now, obviously, we cannot make a linear projection that in yet another 35 years we will run out of water, because the hydrological cycle is a cycle that is renewing itself. But definitely we will have a major problem is that. Many people are already talking about the looming water crisis, and they are saying that water is going to be the biggest problem of the 21st century. Let us examine whether this is indeed true. First of all, what are the drivers that are driving the change, the global change? That starts from population growth, geopolitical changes, technological changes. Look at how much internet changed, how water is being managed, including climate change. But of course, we have to see it very properly. And if you ask yourself the question, what is it that will influence how water will be managed 35 years down the road, by 2050, when we will have 9 billion human beings? The question is, what will influence it most? Will it be the population growth, or will it be the climate change? Who is voting for climate change? Who is voting for population change here? That's absolutely true. So this has to be seen. This has to be seen in perspective. That the climate variability and change is adding as an uncertainty factor to the major impacts the population pressure is causing. So basically, 9 billion human beings, a whole China is joining the demographic situation in 35 years. It's a totally different ballgame as compared to what we have now. For instance, 65 years ago, there were only 8 cities that has exceeded the population of 5 million. What we have today is 80, including the place where we are. So what happens here is we have 3 very important drivers that are driving the change from global down to local. The 3 Ps, as people often talk about it. First of all, and as we agree upon, is the population change. The population change, yes, particularly in Asia, where 60% of the people will be coming in the coming 30s, is a huge factor. Then pollution is the second major driver, while the third one is poverty. And not independent of that is the migration, what we are seeing these days in Europe. That is a much more complicated problem than we have ever believed. So what are the responses of our systems to these global changes? Let us see the responses of the global system, so to say. First of all, ever since the Industrial Revolution, the carbon dioxide release to the atmosphere has been increased exponentially. Over the past 150 years, ever since we have regular climate observations globally, there is a slight tendency of temperature increase globally. That cannot be denied. The nitrogen fixation, anthropogenic nitrogen fixation, has also exponentially increased over the past decades. Also, the nitrogen fluxes to the coastal zones display an exponential growth. Last but not least, the tropical rainforest losses are also exponential. And as a net consequence of that, the species extension is also exponential. So everything seems to be exponentially growing, including the number of McDonald's restaurants and the mobile phones. What is the morale of this story? That age-old assumptions upon which generation of engineers have been trained, namely that the world is stationary, is not true anymore. So the assumption of stationarity is dead. And that has a very severe consequence. Because again, even today, the whole world is using concepts in designing systems, such as, for instance, the 100-year flood, that, statistically speaking, occurs once in 100 years, or the 200-year flood, where we are building up our systems against the 200-year flood that occurs once in 200 years. This is based upon the assumption of stationarity, that the mean of the processes do not change, the variance of the processes do not change, the correlation structure of the processes do not change. And what we see is just the opposite, what is happening. That has been recognized over the past 35 years. And I have to tell you, there was an incredible progress in science since the late 80s, when the early discussion started about the potential climate change. I was at the first, not the first one, that was in Villach, the second World Climate Conference, was in, I think in 1990, where there was still a debate whether the Earth is cooling or warming. There were climatologists who were bitterly fighting against the two opposing views. So a great deal of research program and research money went into coupling the different subsystems, the physical systems, the geochemical cycles, and the human systems, and see how they are interacting with one another. All sorts of scenarios came up, and notably, everybody knows the scenario analysis of the International Panel of Climate Change, IPCC, that comes up with regular assessments of what may happen. What may happen is that if you look at the past 1,000 years and you see the variations of the temperature, deviations from the mean, the global mean, what you see is all of a sudden, very likely, by the end of this century, there will be a range of potential changes in temperature between 1.6 and 6 degrees. Now, I have to say that these are not forecasts. These are not predictions. These are scenario assessments. What will happen if a certain set of conditions will prevail? So this scenario assessment helps to understand the system's dynamics, but not at all it describes really how the system will respond These are potential responses. Yesterday there was a debate, and some people said that, well, the Norwegians will be very happy if the temperature is increasing by 2 degrees, and the Cariocas will, you know, there's a 31 degree or 33, who cares? That's not the temperature increase, which is the problem. The problem is that the hydrological cycle will accelerate. There's a very simple model for that, how the climate is working. Assume that there is a layer, sort of a boundary layer, the layer of the atmosphere. And then as greenhouse gases are being released, not all of them are going through that layer, but a great deal reflects from the layer. That means that the heat in that atmosphere is increasing. Now, if the heat is increasing, then evapotranspiration is increasing. Evaporation from the bare land and transpiration by the plants. If evapotranspiration is increasing, then the probability of clouds forming is also increasing. If there are more clouds, the probability of more rainfall is increasing. If the probability of rainfall is increasing, then the probability of runoff is increasing. If the probability of runoff is increasing, we will have more floods. Quadra demonstrandum. This is how the whole system is working. This is, of course, a very primitive way of doing that, because the system is highly nonlinear. It's a very complex system. There is a great deal of randomness. But this is basically what we are grappling with. Ever since the Industrial Revolution, we were pumping heat into the atmosphere, a great deal of which was trapped there, and that is causing the problem. Not the temperature increase, but the cycle is increasing. So again, the principal message I'm going to leave you with is the impacts of climate change is water and through water. But there we have an opportunity to change things. Definitely something is changing out there. If you look at the various projections or scenarios, there's a huge variation whether you have a 2 degree centigrade increase versus a 6 degree. When we have a 6 degree increase, then basically our systems will collapse. Methane will be released from the permafrost, the whole over Siberia, and that will screw up the whole system. And there's an opportunity that the Gulf Stream would be switched off. There's an opportunity that the big Russian rivers, the Ob, Yenisei, and Lena, will switch off the system. Of course, this is a very remote probability, but as a scenario, one will have to look at it. Nevertheless, something strange out there is happening. What we see is that the very same year, there are huge floods, but also big droughts in space and time. São Paulo, the state of São Paulo, with a huge aridity. The reservoirs are down to 10% fullness. Yet, at the same time, sudden flash floods are occurring. So something is changing out there. Indeed, the question is, and this is what the hydrology profession is grappling with, that is it really true that the hydrological cycle is accelerating? We have all the signs around us. If you recall, I just singled out one year, 2010, the huge flood in Pakistan that basically knocked out Pakistan by causing $40 billion damage. Then the same year, a couple of months later, a never seen urban flash flood disaster in Seoul. A couple of months later, Brisbane, Australia was flooded. Crocodiles were going instead of the motor cars on the street. And they have never experienced anything like that. The World Heritage sites, like Ayutthaya in Thailand, have been flooded, which never occurred since the Thai Empire. Yet, there are some who are skeptical and don't believe in climate change. Ladies and gentlemen, the climate has always been changing. Here the big challenge that the profession has is indeed to prove the velocity or the speed of that acceleration. We know a great deal. We know we can explain with pretty robust global circulation models why the global mean temperature has increased. This is a geodynamics phenomenon. This is not a big deal. We also have seen that the system got really mad around the 20s because there are lots of things which we cannot explain but by the greenhouse gas concentration. It is also clear that reducing emissions, mitigating by setting limits to the energy release, that will not solve the problem alone, simply because the climate system is a huge baby. It doesn't happen overnight, how you change it. It's a very high inertia system. Yet, the best proofs are, if you look at what happened to the glaciers. Over the past 70 years, the glaciers were tracing back. Up until 2 years ago, 2 years ago we made a statement that, clear proof the glaciers were going back. But now, some of the Himalayan glaciers started to grow again. So people should not forget that there's a natural variation, and superimposed upon that is what is climate caused. But no doubt that it may have significant impacts. The water towers are going to be empty if this trend is being continued. This is just an example from Austria to compare the flow out of the glaciers in the 70s and later these days, which means that things are accelerating badly. Some people are basically may I say that the sensationalists are saying that the climate is changing. We are in deep trouble. But ladies and gentlemen, this is not really breaking news, because the climate is changing now for 4 billion years. If there were no climate change, we would not be here. In geological times, there were periods that were much hotter and also much warmer. We are now, luckily, in an interglacial period. If you look back the past 50,000 years, the temperature abrupt changes, but also it took thousands and thousands of years to have that change occur. They occur. If you just single out the Holocene where we are now, again the temperature was much warmer, and then there were even cold periods. Remember 16th century Dutch painting, Breugel. The Dutch were happily skating every year on those rivers frozen. Today, they can do it only every 12th year, because the temperature is going up. But this change is natural, superimposed upon that ever since the Industrial Revolution, the human-induced impact. We have also problems in interpreting data. Yesterday somebody talked about the urban heat island. It's true, many climate observation stations that were set up at the beginning of the 20th century were outside, far away from urban conglomerations. And all of a sudden, those urban areas started to swallow, and they swallowed as well the climate observation station. Therefore, two stations which have a very similar way of displaying temperature changes, all of a sudden they became crazy. In New York Central Park, it all went up. But it shouldn't have. The reason why it went up, because of the climate, the heat island effect. So observations are also shaky, and the word uncertainty is the one that we have to remember very, very clearly. We are dealing with a highly stochastic system that has its own dynamics, but it's very random. The major impact of climate change will be experimented or experienced on rivers. The river regime will change. Yesterday there was a debate that what will happen with the nuclear stations in case of climate change, and that was a sort of a blah blah response given. What will happen is that the low flow will probably go down, and if the low flow goes further down below a critical limit, there will be no cooling water for the nuclear stations. And you cannot switch off a nuclear station overnight. It's a long process. And that is a risk which we have to consider. So observations are extremely important in this case. So far, again, let me just summarize the moral of the story. 90% of the climate change impacts, I will go a little bit further. 90% of the global change impacts is water. And that's where we have also an opportunity to adapt to the changing systems. What is it what we have to do? We don't have too many choices. The only choice we have as humanity is to increase the resilience of our systems significantly. through structural measures, but also via non-structural measures. What are the opportunities what we have here? Each of these is controversial in itself. But if, again, the extremes are increasing, you have to store water for the extremely dry periods. But at the same time, you have to have a space to allocate excess water in case of floods. So humanity needs more storage space, whether we like it or not. It could be surface or underground storage. That's the management tool what we will have. This country has shown a shining example of using hydropower. With all the problems which hydropower schemes may have in terms of ecological impacts and social impacts. But 90% of this country energy is generated by hydro. Groundwater, this is a very, very vulnerable resource, but 95% of the unfrozen water is under the ground. Humanity has a huge adaptation capability if groundwater is used in a sustainable manner. That's perhaps the savior what humanity has. We have Professor Zoya here, perhaps he doesn't agree with me, but let's discuss that. Anyway, more inland navigation. If you go to Europe, east-west, from east to west to the other way around, all the motorways are clogged by trucks. So it's almost impossible. Third message that the linkage between food security, water security, and energy security is storage. That is very, very important, and we have to revisit again that. Of course, storage is changing how the runoff conditions are happening. A good example in the United States. Way back in 1800, there were a couple of reservoirs, a dozen reservoirs on the East Coast. Today, we have 86,000 reservoirs in the United States. This was the backbone of the economic and in many regards the social development. Look at the Tennessee Valley system. And at the same time, climate change will have a huge impact on social stability as rainfall patterns and the GDP in case of the developing countries are highly correlated. There's a 0.9 correlation between rainfall and economic growth. Again, storage, you need to store water. But if you look at what happens today, there's a huge disparity between the haves and the have-nots. The per capita water storage availability in North America is 6,000, in Ethiopia is down to 43 cubic meters. With the Renaissance dam, probably that will change. But again, the storage is a very important component. Energy. Of all the energy produced, 85% is fossil, 20% is renewable, and 3/4 of the renewable is hydro. So nobody can deny how important it is, particularly in case of Africa, where it's only 6% of the total hydropower capacity or development potential the continent has. So nobody can deny the right of the Africans to grow by having stable energy systems. Navigation. It may not be a very nice picture, but if you look at it, which I was referring to earlier, that in river navigation you can have 400 lorries in one push convoy with much less environmental impact than the lorries. Water hazard is a major challenge. This is how I started. This is really the big and most important impact of climate variability in the future. This is the River Rhine looked at from a jewelry shop. Not even the most developed countries, Netherlands in this case, are absolutely secure against the unforeseen events. The flood losses are on an increase over the past decades, and interestingly enough, particularly Southeastern Asia and the western shores of Latin America are vulnerable. Death tolls is increasing dramatically. We have new phenomena as people are moving to underground spaces. All of a sudden, flash floods are just knocking out systems. A metro system in Fukuoka, in 10 minutes, it was kicked out of operation. A very flash flood. The problem here, I was in Prague in 2002 when the huge flood occurred and then knocked out the Prague metro system for half a year. And we had a press conference, and the journalist asked, how often does this happen? I said, well, the learned Czech hydrologist told me it's a 200-year flood. It means that once in 200 years. He said, that's fine. But last year we also had a 200-year flood. Well, I told him that, look, that can happen because of the statistical assumptions that the last year flood occurred in the very last year of the previous 200 years, and to this year is the first year of the next 200-year flood. It was a pretty shaky explanation, but then he said, hey, wait a second. 2 years ago, we also had a 200-year flood. So again, this shows that the assumption of stationarity is basically that. In closing, let me just go to a most important thing, which I think is neglected. Data and measurement. Data and measurement. I indicated before that there was a huge progress over the past 30 years in what we call hydroinformatics, from capturing data all the way up to distributing data and forecast on mobile equipments and all the rest of it. When I started my engineering studies, we still had small-scale hydraulic models. Then when I graduated, the problem was how to solve a very simple differential equation. This was a PhD thing. Today, if you don't know that, you fail. My students were already experimenting three-dimensional models, how the sediment and the water interact. And they come up with very sophisticated models. There's a huge suite of mathematical models. Today, now the problem we have is how to choose the best model. Jokes aside, there are many applications, and again, the numerical techniques have improved so much. You know, we have very precise precipitation forecast. The time lead of hydrological forecast has increased significantly. We had, this is the gray satellite pair, which measures the gravitational anomaly to detect where are anomalies in the gravitation of the Earth, and therefore there's a huge mass, such as, for instance, a huge groundwater reservoir. We have mathematical models which are so sophisticated and precise that they are able to forecast the error which have not even occurred yet. So there's a huge progress, incredible progress in science and technology. Yet, if you look at the data, our monitoring capability is limited. A whole continent like Africa has less data about its hydrology than Germany, about the German hydrological conditions. So the question here, it is an ethical question. How can we trust the global circulation models if the data, if those models are basically calibrated against data from North America, Western Europe, Japan, the Murray-Darling Basin, and New Zealand? The marginal uncertainty must be big. So therefore, this is a common responsibility to help change the situation in Africa. Data is a big issue here, and observations. You know, I have students who are calculating discharge up to the 8th digit, but they have never measured a discharge in their whole life. They never went to a river like an experienced hydrologist who looks at the river and says, more or less by 20-30% accuracy, how much is the discharge? This is a huge problem what we are facing in our educational system. So the whole story started here. In 1992, the United Nations Conference on Environment and Development in Rio. That was the first time I came to Rio and have tested Caipirinha a big time. But since 23 years, a huge progress has happened. We are now just completing the Millennium Development Goals, which we have not reached, but we switch over to the Sustainable Development Goals for the coming 15 years, which probably will shape the future of humanity in a very, very significant way. I'm approaching the end, and that's an important message I would like to share with you, that the time of easy water is over. Water is going to be a very, very important issue. The question is, will there be enough for the 21st century? And what is the way ahead? I think we will have enough water. This never run out. Humanity will have enough water. But we need a number of solutions now. One of them will be here again, not in Rio, but in Brasilia in 2018, the 8th World Water Forum, which will again look at what is the solution. The solution is that we need to generate the political will. This is the key to do it. We need to have the capacity to do it right. And we need to have the resources to do it right now. It was a long way. Again, it was the Future about 2 years ago here in Rio, a very important meeting that has shaped the Sustainable Development Goals, which were adopted 3 weeks ago by the United Nations General Assembly. Closing is, this is our shared responsibility to send the message that the adaptation capability to climate variability and changes through water and through sustainable water resources management. The challenge, what we all have, is how to put water in the minds of people. From the elementary school all the way up to the political level, that it's all about water. And last but not least, the importance of water education, capacity building. And last, let me just quote a message from President Kennedy. Anybody who can solve the problems of water will be worthy of 2 Nobel Prizes, one for peace and one for science. Thank you for your